Hi there, and welcome to our discussion of question 3 in the mid-year exam. So let's continue immediately with that. Okay, a certain water slide, sorry, this is question 5, not question 3. A certain water slide at an amusement park has 3 parts. The first part is a steep slope to gain speed. So in other words, this one, gain speed. The second part is a long stretch where the slider travels at a constant speed. So this is a constant speed. And the final part is a free fall drop into a swimming pool. So okay, and we start off with the questions. Here's the question paper. Questions. Consider a person with mass 70 kilograms sliding from rest at point A and reaching 9 meters per second at point B. Calculate each of the following between points A and B. The change in kinetic energy. Okay, so change in kinetic energy is simply half mass times a change in velocity. Okay, squared. Very important. A lot of people forgot the square. That's critical and will lose you all your marks. So a half person is 70 kgs. And he goes from rest, in other words, future velocity. Remember, change is always future minus initial. He goes from future velocity, 9 meters per second, minus his initial velocities from rest, so 0. And that equals, let's see, 9 minus 0 squared, okay, 81, times 70 times 0.5. Okay, 2835 joules. Okay, next question is the change in potential energy. Change in potential energy is, okay, change in potential energy is mass times gravity. Again, it's changed, so a change in height. Okay, these are constant values. What is changing? Why is there a change in potential energy? The same here. Why is there a change in kinetic energy? Not because the half changes or the mass changes, but because velocity changes. That's why that's a change. Why is there a change in potential energy? Not because mass change or gravitational constant change, but because the height changes. So the first value is mass is 70 kgs. Gravitational constant is 9,8, and then the final answer or the height change is he is 5. He's losing 5 meters per second. Okay, so the vertical drop, okay, first bottom slope, here's all the information. The vertical drop is 5 meters. So minus 5 because I'm losing 5 meters. I'm going from point A to point B is a 5 meters drop. So let me just see if that information is it's not on there, but it is in the sketch. Okay, there's a 5 meter drop there. And so if we calculate that, that is 70 times 9,8 times 5, there we go, is equal to negative. So he's losing 3,450 joules. So minus. So that means he's losing potential energy. And this means he gained kinetic energy. And it makes 100% sense because as he's losing potential energy, the potential energy is converted to kinetic energy. But now what about he's lost more potential energy than he gained? Okay, then kinetic energy was gained. So what is the difference? So if I just add this is how much I lost. What if I just add the 2835, I get 595. What happened to that 595 joules of energy? Well, that's the next question. The next question asks us, what is the work done by frictional forces? So what is happening with all the energy that is lost but not gained by kinetic energy? Well, it is the energy used by frictional forces. So if I say the work done by frictional forces, it would be the change in kinetic energy plus the change in potential energy would be the work done by frictional forces. So 595 is what I calculated. 595 joules. Okay. The difference between these two answers, even if you didn't keep that as a negative. Okay, next question. Using the work energy theorem, determine how long the second slope BC, okay, there's the second slope BC. In other words, we must calculate delta x. Determine how long the second slope BC must be for any person sliding to travel at a constant velocity. This slope has a 9-meter drop in vertical height. Okay, so there's a 9-meter drop in vertical height. How long must it be so that in the end you are traveling at a constant velocity? How long should it be so that any slider, and that's any slider, in other words, mass is not going to have an effect. The only thing they tell us is assume that all sliders experience a coefficient of kinetic friction of 0.22 on the slide. Okay, so first of all, they asked us to use the kinetic energy theorem, kinetic energy theorem says that the net work done is equal to the change in kinetic energy. It comes down to this, that if any forces are doing any work, the net force will cause a change in the kinetic energy, and that change is directly equal to the extra energy. That's basically what this means. The extra energy that there is goes into changing the kinetic energy. Now, we don't want a change in kinetic energy. We want to be going at a constant velocity. Okay? But it doesn't mean that there's no work being done. Well, there's different work. There's a few things doing work. First of all, we have between here and there, what work is being done? Well, what's all the forces for any person that is sliding down here? Well, there's gravity. Okay, so there's work being done by gravity. Is it helping or hindering motion? Well, in this case, he's sliding down, so his movement is down the slope. That means it's helping. I call it an income energy, because we're working with net force and net work done, etc. Gravity is an income. Okay, what else is there? Okay, we've got the normal force. The normal force is the force exerted by the surface. In this case, it's at 90-degree angle. We know that no force making a 90-degree angle does any work, so it's not doing any work. Then there's friction. Friction is always in the opposite direction of motion, so there's kinetic friction in this case, and the kinetic friction will count against us. So in other words, it will hinder motion. Kinetic friction is always negative. There's a different way of doing it. You could just use the angle between the motion of the object as well. So you can use the general formula for work is force times displacement times cos of theta. And then since the work done by gravity is making an angle, okay, and that's the angle we don't know, then that angle would be substituted in there. So we have no idea what this angle is, by the way. All we know is that the change in height is 9 meters. So that does help us, because we're basically working in a triangle here. So we have the opposite side and we have the hypotenuse that we're trying to calculate. So somehow sine of theta is going to come into play here. All I mean in terms of explaining this is that we could have used this general formula and said, well, 0 is equal to the force done by gravity is weight, which is mass times gravity, times displacement, times cos, and the angle between the force. Okay, so where's that angle between the force? Gravity is here, this angle between the force and the motion. So if this is theta, that's 90 minus theta. So this would be cos 90 degrees minus theta. Okay, why not just theta? Well, the angle between weight and motion is not this angle here, it's that angle there. Do you see the triangle there? Okay, so and that angle, if this is 90 degrees then, and this is theta, this angle is 90 degrees minus theta. Add up the interior angles of a triangle, and then plus, and then you could say, what's the other force? Well, the other force is friction. So friction times change in displacement times cos of the angle between the friction, which is now backwards, and motion. So that would be 180 degrees. So in this case, this would become negative f delta x, and we'd get the same idea as what I'm doing here. So here I'm just considering whether or not work would be a positive work or a negative work. Okay, so now if we work out what is the work done by gravity, we know work done by gravity is mass times gravity times change in height. Okay, that's the work done by gravity. And in this case, even though the change in height is negative, it is adding energy to us, so that is a positive effect to our energy. So we must just keep that in mind, that this change in height will be positive and not negative. Minus the work done by the frictional forces is friction times displacement. Okay, and so in this case, friction is calculated, it equals 0. Remember to equal it to 0 because change in kinetic energy is equal to 0. Why is change in kinetic energy equal to 0? Because we want the slider to go down at a constant velocity. Okay, now how would we calculate friction? Well, friction would be mass times gravity, coefficient of kinetic friction, mass gravity times cos of theta. This is because friction is directly proportional to the normal force, mg cos theta. Substituting now in, or at least just that part of it, and I'll tell you now, because at this stage we don't know what is the mass of the slider. We want all sliders to go down at a constant velocity. So we don't know what is the mass of the person, but it doesn't matter. And why doesn't it matter? And let me show you here. Because we've got mass and gravity oh, and sorry, I forgot my delta x here, equal to 0. We have mass times gravity in all of these, in both of these terms. So this term, if I divide everything with mass times gravity, that's perfectly allowed, okay, as long as mass is not equal to 0. I'm not allowed to divide with a 0. So as long as mass is not equal to 0, which we know it isn't because it's a person sliding down there, I can divide that away, and that just simplifies my equation quite a bit, and I can actually substitute from this step onwards. So I can say that 9 minus 0,22 cos of theta, we don't know what theta is, and we don't know what delta x is. Okay, so delta x is equal to 0. We want to calculate delta x. Now, at this point, I'm a little bit stuck because I've got two unknowns and I've got one equation. But cos of theta can actually be written in terms of x, and that would be very helpful, wouldn't it? So, if I go and look at my graph, cos is adjacent over hypotenuse. Okay? So cos of theta is this adjacent side length over my hypotenuse, which is delta x. Which is great because that would actually cancel with that delta x and will actually just leave me with 1, and that's this one. So all I need is this side length here. Now how do I get that side length? Well, I can just use Pythagoras because I've got the other two side lengths. Pythagoras would say that the hypotenuse squared is equal to this side squared plus that side squared. So in other words, I'd have that theta x squared is equal to 9 squared plus this unknown, let's call it adjacent squared. So adjacent would equal to the square root of the hypotenuse squared minus 9 squared. And so that's what will come in here. 9 minus 0.22. This was quite a complicated maths question, which I am not sorry about at all. Minus, let's put 81, good, 9 squared or whatever, divided by this, by that times delta x is equal to 0. And now we just simplify, we just cancel that out. So we have the square root of x squared minus 81 is equal to 9. Okay, so if I just add the 9 on both sides, it will be negative 9. So let's just take this whole term and add it on the other side. So and then it will be positive. So that's basically what I'm doing. If the maths is confusing you, just stop it and the video and see if you agree with me. 0.22 divided by, and then here I'm going to square both sides. So x squared is equal to, I'm going to square this side, 9 over 0.22 gets squared. Why am I doing that? Well, that's how we get rid of a square root, is squaring both sides. And then there was a negative 81 on this side that I'm going to add on that side, 81. And that will give me the square root of x. Square root of x is, let's quickly do that, 9 divided by 0.22 is equal to that, square that, okay, plus 81, good, and then take the square root of that, gives me 41,89. 41,89 meters. That's the question here. You can see this was a massive question, very big question, with a slightly difficult maths problem in the middle. But if this is 9 meters, this must be 41,89 meters long, BC. That's a long slide, isn't it? Okay, next question. Next question. At what height above the water should the second slope stop, in other words point C, for the person in question 5.1, that's this 70 kilogram person reaching 9 meters per second at point B, for the person at point 91 to hit the water at 13 meters per second. So at this point, this 70 kilogram person slides down. At point B, he starts traveling at 9 meters per second at a constant velocity, reaches point C, and then shoots through the air and hits the water. And the question is, how high must that ramp be for him to hit the water at 13 meters per second? So obviously at this point, we ignore air friction, and we're simply considering a person whose kinetic energy at this point plus his, I'm kind of giving it away now, but there were different ways of doing it. The hope was that you would use the conservation of mechanical energy. So if I go here, sorry, I keep opening the YouTube video that I was watching before I made this. It's a good talk, you should go and look at it. Okay, so here we have the conservation. In other words, mechanical energy before is equal to mechanical energy after. Okay, or initial equal to final. Okay, so initial mechanical energy means it's the kinetic energy that it has initially plus the potential energy that it has initially, equal to the kinetic energy that it has in the end plus the potential energy that it has in the end. Okay, final. Okay, so final potential energy, it actually hits the water. Okay, so there's no kinetic potential energy at that point. It's the point it enters the water. So this one will be 0. The kinetic energy he has when he hits the water is 1/2 times his mass, 70, times the velocity that he's going to have when hitting the water. And I think we said that's 13 meters per second. Okay. 13 meters per second, yes. Sorry about that. There we go. 13 meters per second squared. Initial kinetic energy, well, we calculated kinetic energy, the kinetic energy he will have, that's the kinetic energy, the final kinetic energy, we calculated it here, there. So we can just substitute that. 2835. 2835, or you could have calculated by saying 1/2 times 70. And okay, so wait a minute, just why am I using the kinetic energy at point B when I'm actually talking about the kinetic energy at this point? In other words, I'm using the mechanical energy at this point. Remember, mechanical energy is consistent as long as there's no external forces, or as long as it's only what's the word? I'm speaking under correction. I think it's dissipative forces, but it's not coming to mind just now. But basically, what it comes down to, when there's no friction involved, then a mechanical energy that we start with is equal to the mechanical energy that we end with. And here we can see it wasn't true for this portion because there was work done by frictional forces. So that's why the difference here in mechanical energy was actually the work done by all the frictional forces. Okay, so at this point, let's say, so the reason why I'm using the same kinetic energy at this point than I'm using at that point is because he's traveling at a constant velocity over there. So when he comes here, he's not gained or lost any kinetic energy. So the kinetic energy at this point should be the same as the kinetic energy at that point. But you didn't have to know that. You could have just used the fact that he traveled at a constant velocity, so he's traveling at 9 meters per second at this point, which then when substituted gives you the exact same answer. So you could have said that, but it wasn't necessary. Plus the potential energy. The potential energy is his mass times 9,8 times the height that he has at that point. And that's exactly the question that we're trying to answer, is what is the height? What is the height at this point? The height above the water. Okay, so if you used your reference point as the bottom of the pool, which maybe some of you might have considered doing, then obviously you're just adding the extra 3. But the reference point could just be the water surface itself, and the calculation would not change the answer. Okay, so in solving this, we've got our 0.5 times 70 times 13 squared minus this 2835 it's 3000 and what divided by 70 and divided by 9.8 is equal to 4,49 meters. So the height is 4,49 meters. Okay, simple as that. So this height is about 4,49 meters. Now, with that being said, that was important in order to be able to answer the next question, which is the final question. Consider the following table with technical data for different wattage water pumps to pump water from the swimming pool below to the top of the slide. So from the swimming pool below, here's the pump. At point E, it drains water until it gets to the top of the slide, from where the water is then helping the sliders to slide down. And now we can see, well, one of the reasons why it was important to be able to answer the previous question is to know how high that is. So this is about, what's the height? This is 3 plus roughly 4.5. So let's say 7.5 plus 8, that's 16.5, plus 5 is 21.5. Let's do that again. 7, 16, 21.5 And since our table only works in whole numbers, let's go then for 22. So we want to be able to pump the water 22 meters high. So what is this table giving us? Well, it's giving me technical data for water pumps. This is not something that you have to go and study or anything. It's an insight question, or a thinking question, or an evaluation question. We get different wattage water pumps. It's not a calculation question. It's literally reading off the graphs. Okay, we want to pump, according to the table, what is the minimum input power that will be required to be able to pump 1.5 liters per second from the bottom of the 3 meter deep swimming pool to the top of the slide. So we know we want to pump it 18 meters high, 22 meters high, okay, and we want to do 22 meters in, we want to pump 1.5 liters per second. Okay, so at least, okay, so a pump that must be able to pump at least that much. So let's see, 1.5 liters per second means I must divide liters per minute with 60. Okay, so if I do 60 liters, so this one will be able, this pump pumps 60 liters per minute. That's 1 liter per second. This one pumps 1.5 liters per second. So anything higher than this will suffice. Okay, so this one will suffice. And we also want to pump it at least 22 meters high. So anything lower than 22 won't work. And we can see this is the first pump, the lowest wattage pump that will be able to do so is the SM150. And what is the minimum input power required? 1.6 kilowatts. Okay, a little bit out of the box question, not something you could have learned, or it's something that you'd have to just be able to decipher this technical data and spend some time on that. Okay, so that being said, we spent with all of the explanation, and I don't know how much of this might be overtimed, because I did make a mistake and I had to edit out something, but 18 times 1.2, you should have spent 21 minutes on it, and I suspect I spent about 25 minutes on this question with the explanations. I think you should be able to do it in time, but this was a difficult question. I do not blame you if you struggled with this, especially question 5.2 and question 5.4 were difficult out of the box questions. So yeah, but that's how you would approach it. Hope you learned something, and that you understand the question from here.